Let us now move on to the next problem, problem number 24. So what does it say? Okay, so it says, it basically asks us to relate the root mean square speed of hydrogen atoms and helium atoms, but at two different temperatures. The hydrogen atoms are considered at 500 Kelvin, and the helium atoms are considered at 2000 kelvins. So let us first write down the formula for the RMS speed, which is about 3 RT over M. 3 RT over M. Where R is the molar gas constant, T is the absolute temperature, and M is basically specific to the gas. M is the molar mass specific to the gas. So in our case, we have hydrogen atom and we have helium atoms. So, and we have two different temperatures. We have hydrogen atoms being considered at 500 Kelvin. The helium atoms are being considered at 2000 Kelvin. 2000 Kelvin. The hydrogen atom has a molar mass of about 1 U. The helium atom has a molar mass of about 4 units. So now, let us compare the VRMS speed for hydrogen atom with respect to the VRMS of helium atom. And you can see that this ratio is dependent on just two factors. One is, of course, the mass of helium atom over the mass of hydrogen atom. The other is the temperature. The temperature of the hydrogen atom and the temperature of the helium atom. Not the temperature of the atoms themselves, but the temperature under which they're considered. And that would give me a ratio of, so the helium atom and hydrogen atom, the molar mass ratio is 4:1, while the temperature ratio would be 500 over 2000s. That, and you see that would actually come out to also launched 1 over 4. So it's 4 multiplied by 1 over 4, and that is just 1. That's just 1. Square root of 1, which is 1, which means the RMS speed of hydrogen atoms at 500 degree Kelvin is exactly equal to the RMS speed of helium atoms at a much higher temperature, 2000 Kelvin. The RMS speeds are actually equal. And that is our option C. So it says that the RMS speed of hydrogen atom at 500 Kelvin is the same as the RMS speed of helium atoms at 2000 Kelvin, simply because the hydrogen atom is much lighter, about 4 times lighter than the helium atom. And that concludes our problem number 24. Let us move on to problem number 25. Problem number 25. Now this problem is a quantum mechanical problem. It says the normalized ground state wave function of a one-dimensional quantum harmonic oscillator of force constant k and mass m is psi naught x. Psi naught x is the ground state wave function of quantum harmonic oscillator, and its expression is alpha per pi raised to 1 over 4 raised to raised to 1 over 4 times e raised to alpha x minus alpha x squared by 2. Where alpha is m omega naught over h cross omega naught squared equals k by m. K is the force constant, and we are asked to find the probability of finding the particle outside the classically allowed region. So for that, we'll first draw the diagrams. Let's draw the diagrams. So let's say this is the harmonic oscillator potential. It does not look very symmetric, but it's supposed to be symmetric. It's half k x squared. And let's say this is the ground state. This is the ground state, and basically these dotted lines mark the classically allowed region. We mark the classically allowed region. This is x. This is potential of x, and now here we'll draw psi naught of x, which is, if you notice the wave function, it's a Gaussian wave function, which means it decreases. And we're asked to find the probability. Actually, they're both supposed to look identical because it's a non-weighted Gaussian function, and oops, yeah, it needs to look whatever. You get the picture. We are asked to find the probability of finding the particle at the classical forbidden region. This is the classical allowed region. I'll call it CA. I'll call this part the classical forbidden region, abbreviated as CF. And we have to find out what is the probability. Now you see that in the options, the first two options A and B are just two integral values, two integrals. Whereas this option, the last two options are numbers. There is one number which is 0.5, which is option C, or option D, which is 0. Now, as you can see, it cannot be 0 because it's not an infinite square well. So the wave function leaks out in the classical forbidden region, so it cannot be 0, so we rule out D. It can be a number or it can be a function. Now, what we need to do is, there is a very straightforward way of doing it. First, we identify what is the turning point, the classical turning point. This is known as the classical turning point. Classical turning point. So what is the classical turning point? Classical turning point is where, let's call the turning point of x naught. Let's call this x naught, and this minus x naught. You'll see that x naught is where the potential energy must equal the ground state energy. The ground state energy is half of h cross omega naught. That's the ground state energy. And so, if we write down k in terms of m and omega x squared, omega naught squared, that would be half of m omega naught squared x naught squared equals to half of h cross omega naught. And that gives you h cross over m omega naught, or x squared equals to plus minus h cross over m omega naught. And these are the classical turning points. These are the classical turning points. There are supposed to be two of them, and they're symmetrically located. There are two classical turning points, and this will help us. So now the calculations are done, and now the probability of finding it in the classically forbidden region. So you see, psi naught is the probability density. Psi naught times psi naught would be the probability, and mod square psi naught, I'm sorry, that we don't need to write mod because I've already written psi naught star psi naught, which is mod of psi naught square. So that would be probability, that would be probability density, and so our required probability of finding the particle outside the classical region would be that there would be two integrals. There would be two integrals, and one of them would run from minus infinity to minus of x naught. Other would run from x naught to infinity. Look at it closely. One of the wave function goes to minus infinity. The other part of the wave function goes to plus infinity. And the classical turning points are x naught and minus x naught. So one of the integral must run from minus infinity to minus x naught, and the other integral must run from x naught to infinity. And that should give me our probability of existing in the forbidden region. And let's work out the integral. So we see, if we substitute this alpha by pi, comes out to be 1/2 because it gets squared, and there's minus infinity to minus x naught, which is minus alpha x naught squared by 2. Alpha x naught squared by 2, but it's not 2 anymore because we squared it. It's just alpha x naught squared, because it's alpha x naught squared by 2 times alpha x naught times e raised to minus alpha x naught squared by 2. So the half goes away, and here we have x naught to infinity. Alpha x naught squared is dx. Now this integral can be simplified. The rest of this is about simplifying the integral, and we don't have any tricks or any shortcut method over here. We just have to work this out, but I promise that it is actually very simple. It's very straightforward. There are not a lot of tricks to actually consider. So let me draw it out. Let me write out the turning points again once more. And PCF, what you have to do now is make a variable substitution. The variable substitution, remember, I'll write it out again. Alpha, remember alpha was m omega naught by h cross. That was alpha. So what I'll write is, let square root of m omega naught by h cross, square root of this will equal to some variable y. Square root of this. And it will be clear why I'm doing this. As you see, if I write out alpha here completely, m omega naught by h cross pi, it's half. And this, I'll not write it both times because they're the same. This comes out to be m omega naught x squared over h cross to the x. Now we write this. Now be careful, the x is not under the square root. Only the part m omega naught by h cross is under the square root. If we take the dx times m omega naught over square h cross would be dy. And you see, that's exactly what we have here. We just take this inside the integral. On the other hand, if we square both sides, see this becomes m omega naught x squared over h cross, which is what we have in the exponent of the exponential, and therefore our integral simplifies to 1 over square root of pi, because square root of pi, there is no pi here, the square root of pi remains outside. But now, this minus infinity to x naught plus x naught to infinity, it's e raised to minus y squared dy. It's amazing. Now we just have a very simplified quotient function just with a variable substitution. Now there's just one more step that we need to do, and which is, we are lucky that we can do it. We just need to show that these two integrals are actually equal, as in these limits can be actually transformed to these limits. And by the way, these limits have to change. These limits are also changing now, because now if we substitute x naught, this goes to minus 1, this goes to plus 1. We have to substitute x equals to this here. So limits and infinity remains infinity, of course. And now all we have to show is minus infinity to minus 1 e raised to minus y squared dy is actually equal to 1 to infinity e raised to minus y squared dy. So how can we go about this? It's another variable substitution. This time it's even simpler. Let y equals to minus of z. Let y equals to minus of z. Then dy equals minus of dz. You see, this integral becomes infinity 1. The exponent is squared, so putting a minus sign makes no difference. But now we have minus dz over here, and you see that minus dz can be flipped if instead we simply interchange the limits. It becomes minus z squared dz. The minus sign is gone now. And so these two integrals are really equal, and therefore our final expression, ECF, is basically the square root of 2 over square root of pi, because these two integrals are the same, so it's 1 plus 1, so it's 2. It brings the 2 in. 1 to infinity e raised to minus y squared dy. And we see that there is an option with the exact same expression, and that is b. So our option to mark is b for this question. That concludes our problem on quantum harmonics. It was a bit long, but with the right techniques, you can basically simplify it very, very quickly. So that concludes problem number 25. Let's move on to problem number 26.